then in the afternoon session today, I want to tell you a little bit about numerical inference. So having seen now how Bayesian inference works in fairly simple models, simple in the sense of models that use probability, mass, and density functions that have nice mathematical properties, because of course one very nice thing about the normal or Gaussian distribution is that doing things with it is relatively straightforward. We are starting to consider models that may not be of that simple form. That said, I think these parametric, relatively simple models, they usually have good motivations, and of course, one of the, in terms of likelihood, one of the core motivations is, of course, the central limit theorem for Gaussians. So this all makes a lot of sense. So there is not, just because it's mathematically handleable, or whether or treatable or whatever, doesn't mean that it's bad and that one needs something different. But one may or may not have good reasons to use probabilistic models that are not of the conjugate form. And for this, if one still wants to do a Bayesian inference, there are ways to usually then approximate the posterior distribution and things that follow from it. And the two main methods that are out there are numerical inference methods that are usually labeled MCMC, and the other one is variational inference, and this will be the topic tomorrow. So the first thing that I want to spend some time on is to discuss what's actually the motivation for using numerical inference. So where's the problem? What is the problem? Why do we need numerical inference? And then, depending on, so I don't think we will discuss everything here on the list in full detail, but follow a down to basics approach to numerical inference, because if you, I don't know, go to machine learning summer schools or open psychology books on Bayesian statistics with Stan or JAX or Bucks, you get the impression that you always then need random number generators, and that's the only way forward, or at least that's sometimes how I felt. Although, for example, the book on Bucks, which is Gibbs sampling software, also makes clear that you not always need MCMC or Monte Carlo methods for Bayesian inference. There are even simpler things, namely analytical things like Quadrature and Laplace Approximation, where you don't need a random number generator. And if you use a random number generator, the question is also, what do you do with it, and what's actually the purpose of this? And that's then a little bit on Monte Carlo integration, important sampling, and acceptance rejection sampling. What's not in here is actually the most general tool to this end, Markov chain Monte Carlo, so MCMC, because basically I haven't really worked myself through it, but I know that it's only sensible to consider it and appreciate it if all these things that we have on the list here fail, and then it can help. And we also see some of the shortcomings of things that we discuss here. So one gets the feeling definitely after this lecture that, yeah, that's okay, but it's only solving part of the problem here and there. So is there something more general? And apparently MCMC is that. How exactly it does it and so on, I don't know. As I said, I'm more from the variation inference world and not from the MCMC world. But yeah, at one point I will also do MCMC, but I know if I want to explain MCMC to anyone, including myself, I need to first explain these things to myself. Otherwise, I don't know why I'm doing MCMC. So why? What's the whole purpose of this? What's the motivation? And the motivation here comes with a new random variable that you might not know. So at least for me, it was not the. So I think haven't really dealt much with Cauchy random variables. However, they exist. So there are so-called Cauchy random variables, which have a specific parametric form. They look a little bit like Gaussians, but there's no exponential in there. So there's this y minus theta. Theta is one parameter here. Y is the random variable. There's s, which is a little bit like the variance parameter. And then there's this normalization factor. And the way these things look are a little bit like Gaussians, but with heavier tails. So if you have here this Cauchy random variable or this Cauchy probability density function with theta parameter 0 and s parameter 1, this looks a little bit like a Gaussian in a way that a t-distribution might also look like a standard normal distribution, but not quite. So it's not as round here. It has a little bit more probability density here. Why do I talk about Cauchy probability density functions? Because if in the model that we just looked at, namely, there's a typo. If we consider, maybe that's not a typo. No, there's a typo. If we consider the model that we just looked at, but now we want to use a different likelihood, namely we want to consider also a Gaussian prior, but a likelihood that is Cauchy, because, for example, we want to model a phenomenon where we are not happy with the fact that extreme values have fairly low probability under the Gaussian. So we want to use a Cauchy random variable. Then we get into a scenario where we can write down the posterior distribution that leads up to a proportionality constant. So here we put, so there's not a typo, I was just confused. Here we have the prior, so that's Gaussian, and here we have independent samples from Cauchy distribution, so that's again where the product signs come in. This whole thing is proportional to that. Now, if we wanted to really do Bayesian inference, then of course we needed to find the integration constant, like we did in the beta binomial and in the Gaussian model, just by looking at the product of prior and likelihood, and then figuring that this looks strangely familiar, so it looks like a Gaussian or beta, so we know what the normalization constant is. Somebody worked out that integral. Now, why I brought up this Cauchy distribution here is that this thing here cannot be integrated analytically. So one can only ever approximate this integral here. This is I'm just telling you that, so I'm not proving that, but it's actually not that rarely that this happens. An example that you all use all the time for a function that is not analytically integrable, I'm not sure whether that's the correct English word, but that cannot be integrated analytically, is the Gaussian itself. So the CDF, the cumulative density function of a Gaussian, there is no closed form solution for that. Whenever you use the cumulative density function of a Gaussian and evaluate that, that's done numerically by approximating the integral. Certain things are just, you cannot, there are no analytical solutions for integrals. In this case, then, of course, what I mean always are these improper integrals from minus infinity to infinity. There are just functions where Riemann integrals are not defined, and improper integrals then might even not be defined if definite integrals are defined. That's, of course, to show that something cannot be integrated. That's quite some effort, and one needs to delve quite deep into things. So that's what we are not. That's not something that we are doing here. So the other reason why one might want to use something like numerical inference or variational inference is that one doesn't want to try to analytically integrate. So often you come up, or people can come up with models, and then you can now sit down and try to figure out whether you can integrate that analytically with the methods that are at your disposal. So that would be for finding the antiderivative and then doing the limiting or the limit processes so that you find normalization constants. But of course, this takes a lot of coffee and a lot of thinking and a lot of time, and maybe you're just not into it. And especially if you know that well, it doesn't really matter. I can just use a numerical approach to integrate this, and then it's as good as if I found it analytically. It might be at the 10th decimal place, there might be something off, but that's it. So that's then a motivation to go to numerical inference procedures, which all deal essentially with the denominator of Bayes' theorem, namely this integral. So recall again that the so we're now looking at the slide properly. The posterior distribution, that's what we want in Bayesian inference. The prior and the likelihood, they don't come from anywhere. We decide what they are. So we decide we want this kind of data distribution because we want to allow for random error around some function or something like that. And that's then how we consider the data to be distributed. And we also decide on a prior. So our likelihood has some parameters, and we decide on a prior for these parameters, and we set them as we like to. And then we have to find our probabilistic model. And as I already said, then forming or looking at the posterior distribution in terms of its unnormalized version, so not integrating to one or not summing to one, we can already do. I mean, we still, if we now fix the yi's and the mu and the sigma square, so we set our prior parameter sigma square and mu, and we fix our yi's, we can of course look at the shape of the posterior distribution, and we can read off maximum a posteriori estimates. But we don't have, we can't really, we can't form credible intervals, and we also, what's the other thing that we can't do? Yeah, we can't really compute expected values or variances on this because it's not a probability density or mass function. It's just a function, but it doesn't integrate to one. And hence the core problem in Bayesian inference is this integration, because to find this the posterior in terms of its profile, that's not a problem. The problem is because that's just already in the definition of how we set up the model. But the problem is to find this normalizing factor, which is P of y, which is the marginal of the joint distribution when integrating out the parameter. And hence the problem is a problem of integration. If this is not analytically possible, so you can look up if you want to figure out or want to know why you have this 1 over square root 2 pi sigma square factor in the Gaussian. Well, that has to do with the Gaussian integral, and you can find proofs of how to derive this integral. But for things like this might not exist, or nobody knows it. And then if you still want to do Bayesian inference, then you can use numerical integration. Another reason where you might use numerical integration is that you may in fact be able to derive the posterior distribution, but then you want to evaluate some function of the posterior distribution. In the easiest scenario, of course, the expected value. So you might have a probability density, but then you want to compute the expected value or the variance as point estimates, and or even again credible intervals. And these things are then also integrals and may not be analytically easy to solve. And this is again a reason to use numerical integration. So the whole problem, this is also why we spent some time on integrals on Wednesday, so yesterday, is a problem of integration. Really the integration that you know from school. And per se, to solve this kind of numerical integration problems, you don't need MC Monte Carlo methods, which are always associated with random number generators, but there are other ways to do numerical integration. And the more basic things I want to tell you now, of course, all of these things can fail. And then, of course, there are benefits to use more sophisticated methods. That's why these methods have been designed in the first place. So somebody had a good reason to propose something new. But it doesn't mean that for the model that you are working with, that you have designed, you necessarily need the most complex way to integrate things. So the thing that I meant earlier in terms of the proportionality, and that you can find, of course, the functional form of the posterior that's also visualized here. So here we have the prior, that was Gaussian. We have one observation that was Cauchy distributed, and you can, of course, write down the posterior probability density and also evaluate it using R in this case, and you can plot it. And you see essentially what's going on. So here, what is the scenario? So the prior was centered on 0, the variance was 1, and you make the observation 2. And then if you look at this this function here, you see that a lot of not probability density, but a lot of area under the curve is located here towards 2. It's a little bit, of course, also biased towards 0 because this doesn't have the biggest variance. But yeah, you can plot it. You see essentially what's going on, but this function that you see here is not a probability density function because it doesn't integrate to 1. This one does, and this one does as well. So it's just not a probability density function. That's the problem. It's not that you don't get an intuition about what your most likely parameters are. It's just that you need to scale this properly so that it integrates to 1, so that you have a probability distribution. Good. And maybe before we do questions on this, the things that I can or that I can show you in principle here, although I guess we don't have the time for everything, is first of all quadrature approaches. This is classical numerical integration using Riemann sums, and it makes a lot of sense to look at that. The Laplace approximation, which is for people from cognitive neuroimaging interesting because, well, it shows up everywhere, the Laplace approximation, and it's often fairly communicated fairly unclear. So I think we will at least have a look at it. We might not go through the derivation or motivation of it, so how it works, because we also need the Taylor's theorem there and so on. But it comes up everywhere, Laplace approximation. The scheme or the paper that is very linked to the free energy principle. So I think it's called variational Blaze, and the Laplace approximation. That's a different Laplace approximation. Carl means Gaussians there. It's not this Laplace approximation, but it's still good to know what the differences are. And Monte Carlo integration, and that's kind of then showing where the random number generators come in. Then the random number generators can be made more versatile. I mean, the question is, how do you generate random numbers in the first place, and how do you get random numbers that are distributed according to something that you like? And this is what different sampling algorithms do. And what we don't do, although I might here and there say something about it, is really going to the pros and cons of different methods. Although you will see that certain methods just don't work for certain problems. And as I said, MCMC is not a topic here. Maybe in some later workshop in my life. Good. So that's the motivation. So do you have questions about why we talk about numerical inference at all yet now that we talk about Bayesian inference?
Not directly, but I have something related, if that's okay. So I still have a problem in understanding where the integral really comes in, because when I think about the conjugate inference that we did before, you mentioned integrals, but I don't really remember seeing the integral sign. We really just worked out the posterior distribution the way I understood it as like the product of the likelihood and the prior, and kind of ignored the marginal probability as it's just a normalization factor, right? So I don't quite understand where the integration comes in and why it's important.
No, so it was there. It's always there, but it was because we were dealing with these relatively simple or these kind of standard distributions. We didn't have to do the integration because we know the result of the integration already. So if you think of so consider here the Gaussian. So the action in the Gaussian is in this exponential term. Yeah, so it's a function of y, and sigma square and theta are fixed, and if you change y, you get this bell-shaped curve. Y is on the x-axis. You change y, you get different value of the function, different probability density. Now, this term here, this exponential of -1 to sigma square y minus theta sigma square, this thing, if you form the this thing does not integrate to 1 as an improper integral from -infinity to infinity. However, it integrates to something that is known, namely it integrates to square root of 2 pi sigma square. So if you sit down and work out, and you can find proofs on that, it's I think it's called Gaussian integral. If you Google that, you find proofs, which have been around for a long time, of course, on how to integrate this term here from minus infinity to infinity, and the result will be square root of 2 pi sigma square. And now this thing, to normalize this so that it integrates to 1, or to get this whole thing, is that, of course, in terms of the linearity of integrals, if you now put the integral sign here where I point with the mouse, this term here is not dependent on y. You want to integrate over y, so you can take it out of the integral. This thing will integrate to square root of 2 pi sigma square, and then you multiply it by 1 over 2 pi sigma square, and then you get 1. So this is the normalization factor of the Gaussian. Its only purpose is that if you form the integral of this function here from minus infinity to infinity, is that you get to 1. Now, why didn't we have to integrate anything in our conjugacy models here? The reason was that we rewrote this proportionality in this form. So we rewrote it as exponential of minus 1 to phi 1 theta minus phi 2. And we could rewrite it like this because we defined phi 1 and phi 2 in a specific way. Now, if we see that we have a function like this here, and we wonder how to normalize that, meaning that we want to compute the integral from minus infinity to infinity, we can, of course, we look at it and we realize, this is just the same thing here as this. It's just that instead of sigma square, it says phi 2, and instead of theta, it says phi 1, but it's actually exactly this function. And for this function, we know what the integral is, namely it's square root 2 pi, this value here. So that's then, if we are here, solving the integration is easy because we know that the integral of this is square root 2 pi phi 1. And then we already found the normalization value. It's just that it's known in the mathematical literature that the integral of this thing is square root 2 pi phi 1. And this is, at this point, I mean, if we really would spend a lot of time in this workshop, I could have at this point said, okay, so now we have to integrate this. And then we could have, so I think it's one way to do this with polar coordinates and so on. So we could have spent some time now, first but then also showing this with the limit process, spent some time to do the integration. However, this integration was done long time ago, so we didn't need to do it, but it was there. And the same goes for the beta binomial. There we had the same thing. Also here. Here we end up with something that looks pretty much like a beta distribution, but without the normalization factor, which is this gamma thing here. So we end up in the proportionality with this, and this gamma factor here, we then know, okay, there's this -1, but this alpha and this beta, they have to go in there. So that's again where the integration there happens. Yeah, did that make sense?
Yeah, that makes a lot of sense. Thank you. Just one quick follow-up. So basically, we need the integration for in this case at least, finding the normalization constant to ensure that we have a proper probability distribution.
No.
And then to be able basically to calculate a probability for a certain interval.
Exactly. Yeah. So that's the whole motivation. So like I said, so if you look again at this, oops, I'm zooming here. No, that's my cat. What happened now? Now the cat has destroyed everything. I don't know why this is not going away. It's to say what has the highest density, you can read it off there. The proportionality constant, that's just a number, right? So you multiply each of these values by the same value. So all of these values get, so what changes if you multiply this, the only thing that changes here is what you see on the y-axis as values. It's the only thing that changes. So, but as you correctly said, we cannot compute probabilities from this because this whole thing doesn't integrate to one. So we can of course compute well, if we could compute integrals here, but then we get numbers like I don't know, 2.5, and then that's obviously not a probability. So that's the whole thing. So it's really yeah, it's not as awesome as sometimes it sounds. That you use stochastic simulation and MCMC. It's just really the scaling of the function. Yeah.
Yes, thanks a lot.
Good. Now, how can we integrate something? And let me just check. Just want to check. So there are different ways to compute integrals numerically. So you, of course, and so me, we know how to compute integrals using antiderivatives for definite integrals. The question is how to do numerical integration. We know how to do it analytically. We don't really know how to do it for improper integrals, but we know it for simple functions. And now we want not use our analytical skills and finding antiderivatives, but use it numerically. And one way to do that is called quadrature. And essentially, this is using the idea of the definition of the Riemann integral as a limit of Riemann sums. And that's what quadrature is about, and that works. And yeah, let me show that to you, what that means. So quadrature is the same as numerical integration. It's just the name is quadrature. I found that a little bit confusing because there's numerical differentiation and numerical integration is called quadrature. It's a big topic, or it's one of the topics in numerical mathematics. It works well, so it doesn't solve all the problems of the world. It works well if you have univariate functions, then it usually works best. And it already has many different, there are different flavors, different forms of quadrature, and here some are listed. So if you use numerical integration in your favorite work environment, I guess it will usually implement something more fancy than Riemann sums, but we will look at Riemann sums as an example. So what is this? So maybe let's look first at the picture. So you all know that an integral is the area under the curve. And if you want to solve an integral or integrate something numerically, of course, you can put rectangles under your curve and make these rectangles smaller and smaller. You have different, there are different options how to put the rectangles under your function. So this is why there are then different rules, like the left rule, the right rule, and the midpoint rule, where here the left part of the rectangle touches the function, and here the right part, and here the midpoint. This is formalized as shown here. So we have a univariate function that takes on real values. We take a partition of the interval that we want to integrate over. So this now is essentially talking mainly about definite integrals, how to deal with indefinite integrals. That's not really addressed here. However, if indefinite integral, improper integrals is not really dealt with here. However, if they converge, also these numerical approaches can give you results there. So the partition here is the partition of what you have on the x-axis, and that's these intervals. The Riemann sum over this interval AB based on this partition is just the sum of the products of the width of the intervals, so the width of these bars multiplied by the function that you're trying to integrate at some location between the bounds of the interval that you're considering. And I already showed you 3 different things that you can consider. So you have an interval from 1 to 1.5, and you can evaluate the function either at 1, or you can evaluate it at very close to 1.5, so that, or for this interval at 1.5, so that that you do it there or in the middle. Of course, there are more options. You can essentially evaluate anywhere there. This is why there are different rules, so left rule, right rule, and midpoint rule. The thing is, regardless essentially of what you do there, if you make the width of the integral, the width of the interval, not the integral, of the interval smaller and smaller and smaller, this sum here, setz sie doch mal hin, ey. This sum here converges to the definite integral that you're trying to find here. So this is actually what you did in school when you introduced the Riemann integral in the first place. You said, okay, we want to compute this area under the curve. Now let's put rectangles there and make them ever smaller. And that's what is called quadrature. Of course, there are then different ways and different things to make things better, but essentially that is it. And as I said, it's getting more applied. So we didn't see any computer code in the last hour because I don't show you the figure code. Of course, I created these figures, but you find this in the R Markdown code for this course. But the calculations, I didn't show them how to do them in programming, like 18 plus 1. We don't need to write a program. Here, I'm using the quadrature approach that is implemented in R. That's the integrate function. That's how it's called. And you give it this integrate function, you give it a function that you want to integrate, its boundaries, where you want to integrate that. So in this case, I want an improper integral from -infinity to infinity. And then you might have additional parameters of this function. So what I'm doing here is I want to compute the integral of the Gaussian PDF over the whole real line. And there's this integrate function. I put in the function that I want to integrate. That's the Gaussian here. Then let's have a look what we get. And we get 1. So that works. Here, an integral of the Z distribution, if you want. So the standard normal from -1.96 to 1.96. If you integrate that, you get 95. And then other examples here are the expected value of the Gaussian. I basically wanted to check whether I used this integrate function correctly. The expected value of a Gaussian with expectation parameter 2 and variance parameter 3 yields 2. And the variance here, so the integral of x minus its expected value parameter squared, also over the entire real line yields 3. So so this was kind of a validation of the my use of the integrate function, but you see that these that it's relatively straightforward to use. You just need to specify the function that you want to integrate and then call it. And if this function has additional parameters, you can also put them in. And here I then applied numerical integration to the function that we came up with here. So the product of the Gaussian prior and the Cauchy likelihood to actually where are we? To evaluate a posterior probability. So what's so basically that's not quite it. First of all, trying to integrate the whole thing from -infinity to infinity, which doesn't work because so this problem with the Cauchy distribution is actually deeper because also this thing, this probability density does not integrate to anything. So that's this Cauchy distribution is a horrible distribution, so don't use it. The expectation and the variance of a Cauchy random variable are not defined. It doesn't have an expectation because this integral does not converge. This has to do with the improper, so you have these limits and you know that not all sequences converge to something. So the sequence I plus 1, I plus 2, and so on, that does not converge. Other sequences converge, so 1 over I or something like that converges, but other things not, and the Cauchy thing just doesn't converge. And so there also the quadrature does not really help, and I doubt that anything helps. So here, to get at least a little bit into the direction of inference, I tried to integrate it then not from infinity to infinity, but on a relatively broad interval given this look, although I'm obviously, well, -2 to 2. I'm just normalizing this part here of the, so up to 2 of this posterior to have a probability density function there on this part of the parameter space. I know it's not perfect. I was a little bit unhappy that so using Cauchy distributions is just a bad idea. One needs an example where there is an analytical solution, but it's really hard to derive it. But that's, of course, if it's there, then derive it, and if it doesn't exist, then also this quadrature doesn't really help much. But at least for parts of the parameter space, it can help. So if you then use the improper, instead of using the improper integral, you use an integral with very large boundaries, then you get to something almost like at least you get it to a probability density on some interval that you might be interested in. So to normalize the posterior on -2 to 2, you need to multiply the whole thing with 0.373 because that's the integral there. And if you now normalize this, so that's what's happening here. If you multiply here, so that's where, so I'm normalized from -2 to 2 and multiply the posterior PDF that is only proportional by this 1 over this integral, which I call Py here, then on this interval, so from -2 to 2, there's a proper PDF. It's not awesome because it's just then somehow proper inference for a limited parameter interval. Although that said, if you, where are we? If from the beginning you say you are only interested in parameters in a certain interval, so, and this is not that so if you look at learning rates or stuff in cognitive neuroscience, it's actually not that uncommon that you have boundaries for your parameters from the very beginning. Then this approach also does not hurt much if you know what the boundaries are that you want to look at and where you want to have a probability distribution over later on. But it's not awesome. I need a better example where it's still hard to come up with an analytical solution, but there is a analytical solution for the thing. But then you don't need to actually use numerical approaches or use quadrature. So it's not the most awesome example. A better example is actually, or if we would have a probability density. So if we are in this Gaussian scenario here, and we wanted to compute the expected value. So if we would have worked out the normalization factor, because that somehow works analytically, but then computing the expected value does not work. That would be something. This same thing is actually the CDF of the Gaussian. So there you have a proper probability density function, everybody use it, but to integrate this from minus infinity to a certain value, that's just not analytically possible. So there you also then need quadrature. Yeah, so that was me trying, so yeah, give an example for integration using quadrature, which, if you think about it, does not really help in this case because you can't really solve this in proper integral. But if you could already solve this in proper integral, then there would not be motivation to use this in the first place. So I think Laplace approximation, has a different approach of dealing with integrals and maybe gets us around that. But so what I want to convey is here, numerical integration does not mean MC-MC. There are other ways to do numerical integration, and the much more classical way where you don't need random numbers is quadrature. So after the break, I will then briefly talk about Laplace approximation and then show you Monte Carlo integration as an approach that is uses random numbers and to see how this is motivated, which one can also use. But if you go to machine learning summer schools or things like that, everything will be Monte Carlo estimates and MC-MC. Most of the time, I think you don't need this. Okay, questions right now? Okay, so if you ever want to solve an integral of a function, use the integrate function, so definitely a definite integral or even an improper integral if you are lucky that it exists. Use the integrate function in R or in MATLAB or in Python. Can just integrate functions with that. Of course, this works for univariate functions very well. It doesn't really work well for multivariate functions. And then, of course, Monte Carlo integration can again be something sensible. So it also depends, of course, on the dimensionality of the parameter space. And if this is large, then yes, quadrature might not work computationally efficient anymore. But then maybe so doesn't do Monte Carlo integration. Okay, let's have a break and in 15 minutes then do the last session for today. That would be 2:40. Let's continue at 2:40. Okay, then for the last 45 minutes or so for today. Yeah, we will look at two other approaches for numerical integration, which are different from quadrature. So quadrature basically using the definition of the Riemann integral in terms of Riemann sums to do integration numerically. The Laplace approximation, I think in flavor, it's a little bit like a Taylor approximation. So you use you approximate something, so a function that you want to evaluate or whatever, by another function which is almost like your function, and here you do that in terms of integrals, and Monte Carlo integration, which then uses random number generators. So what is the Laplace approximation? So the Laplace approximation is a method to approximate posterior expectations of this form. So that's one way to frame it. So if we have posterior density p theta given y, and we want to evaluate the expected value of some function of the parameter, for example, just the posterior expected value where we have theta here, or, and this is not on the slide, but I think it also works, although this is of course taken from some book. If we just, if this function here, f of theta is just 1, so if we just want to integrate some function over theta, so to find a normalization constant, I don't see any reason why the Laplace approximation shouldn't work also in this case. So I present it here as you know the posterior density and you want to evaluate its expectation, and somehow that is not simple, so we use an approximative method. I'm not quite sure that this would not also just work to derive the normalization factor or to approximate the normalization factor, but we can have a look at it if we look at the details why this might not work, but I think it works. So the if this function f here is just a constant 1, then we just integrate this thing here, and I don't necessarily see that this has to be normalized. So how does that work? And let's first maybe, or maybe it is required. I'm just checking what I see. I don't. I'm not really sure whether that works for the normalization constant or not. It works for expected values. So what's going on? So we start again from a probabilistic model, p theta y. We write down py given theta and p theta, so the likelihood and the prior. In this case, we're dealing with a scalar parameter. And this is not really nice. I will correct this. It's a little bit confusing, but it's in terms of the probability densities, everything is fine. And we are interested in evaluating the posterior expected value. So the scenario is here, we want to derive a base estimator. Yeah, we want to derive a base estimator, and what we don't need actually to derive a base estimator is the functional form of the posterior distribution. So if our aim in Bayesian inference is now not to present a nice posterior distribution, but to give a base estimate, then Laplace approximation is something very reasonable to do. We don't get the posterior distribution from this thing, but we get a base estimate. And as we discussed earlier, base estimates might be useful instead of maximum likelihood estimates. Now, so we want to come up with a base estimator. So we want to have the expected value of some function of theta, maybe just theta itself, so the identity function under this under the posterior distribution, and the result of Laplace approximation is the following. This integral, so this expected value, is approximately given by this thing here, where we see some kappas and we see some h's and some theta tildes. So the question, and some h's, some theta tildes, and the question is, of course, what are these things, and how do we not need the posterior density if we want to evaluate a base estimate? So these H1 and H2 things are defined here. So they are the logarithm of the function that we want to integrate. So for example, theta, or if theta, let's not go into my normalization factor again. The function of theta, or just theta, the likelihood and the prior, so the likelihood, probability, mass function, density function, and we should deal with density functions here. So the likelihood density function and the prior density function, and H2 again uses the likelihood density function and the prior density function. So everything that we have in terms of this H1 and H2 we get from our definitions, and there is no we don't need p theta given y I or y all the y's here at all. And then there are these two kappas here, so and also these tilde points. So the tilde points are these function evaluated at the minima of H1 and H2. So they need to be found somewhere, somehow, maybe by numerical optimization. And these kappa values that are written down here are the second derivatives of H1 and H2, again at this minimum points. So this finding these minima of these functions here. So these functions we can define in terms, or we can write down in terms of our probabilistic model. Finding the minima might again be hard, and finding the second derivative at the point of these minima might also be hard. But this again then can be done numerically. The question is, of course, why? So the result is, okay, we can use this formula to approximate this. Question is this a good approximation? The answer is yes, if the n is getting large. So for a lot of data, this approximation makes sense. And of course, the bigger question is, where do these formulas come from? Why is this working? And that's explained a little bit around these two, or this slide here. So this formula comes from, essentially it's an application of Laplace integral approximation method. So if, so that's again then an old result, if you have a univariate real-valued convex function, and this is twice differentiable and has a minimum, then this integral here, this improper integral of the exponential of this function, so this function here is free, but you have to put into the exponential and multiply it by minus n. This improper integral can reasonably approximate it by the value of the exponential function at a minimum of this function times this constant here. And essentially what this rests on is a second order Taylor approximation of f in the in this minimum, and the fact, again, the Gaussian integral, that this improper integral is known to be square root of pi divided by a, or pi times a if we would have 1 over a here. So that's again the thing that is useful, that is used, or that's the Gaussian integral. So the motivation for Laplace integral approximation method, not showing that it's getting better for higher n, but at least motivating in terms of a second order Taylor approximation that's shown here. If you don't know what a second order Taylor approximation or what a Taylor approximation is, that's approximating the value of a function using a linear function around some point, and second, so that's first order Taylor approximation, and so a linear fine function, and second order Taylor approximation then uses the squared function. The point is here more that we, what is the point? The point is that we define our probabilistic model and we get an analytical approximation of this integral from math, essentially. I think that's as deep as we can go here if we don't want to spend more time on it. So the use of Laplace integral approximation method then in the context of the problem that we have here leads to these two functions in this formula. Yeah, so the point, what's the point that I can make without discussing that further? The point is, I think the point is already in this formula. So there is this formula that you can use where you don't need the posterior density. So you don't need to derive it to get the expectation of the posterior. And if I'm not mistaken, you can, I wonder whether somewhere the fact is used that these things, namely this and this, are densities, and I don't, so that would, the use would of course be that they integrate to 1, but I don't see that this is used anywhere in the proof, so I don't see a problem of also using this for deriving the integration constant. I should really put this on the slide as well. So you, what's happening there is essentially like in the scenario of a Taylor approximation. So instead of using the function that you actually have specified, you use a function that is very similar to it, and you use the properties of that function in terms of its integral to say, okay, the integral of the function that I actually want to integrate is approximately this. So that's Laplace approximation. It's often stated a little bit, in my opinion, too simply, is that you approximate the integral with a Gaussian. And yes, the Gaussian integral is coming in, but it's not that it's really that simple as putting a Gaussian somewhere. At least not in this presentation, in the way it's formed here. Maybe one can make this argument, but yeah. That's so the really thing to get the integral is not putting a Gaussian somewhere, but to use these functions and their respective minima and so on. That's Laplace approximation. It's actually not that trivial, but it's to motivate and to derive, but in the end, it's a analytical formula to approximate an integral. That's in the end what it is. So I guess this raised more questions than answers, but actually I want to leave it at that. Yeah, so you will come across it. And if you then want to figure out what Laplace approximation is, look into these slides, and then you get the gist of it. And I've seen worse presentations of Laplace approximation than this. So this is taking a little bit from the what's it called, the Held book, and by Leonhard Held, and mixing that with yeah, some more basics on the Laplace integral method. So the last thing that I want to discuss is Monte Carlo integration, because that's, if you look at numerical Bayesian inference, that what everybody seems to be mainly concerned with. So people don't talk much about quadrature, people don't talk about Laplace approximation, but Monte Carlo integration, so using random number generators, that's big on everybody's mind. And I think one of the reasons for that is that quadrature and Laplace approximations work well for low-dimensional parameter problems. So if you have very few parameters, then this works and is computationally doable. As soon as the parameter spaces get larger, so you get to more complex models, that might not work that well. Although it's then also always said that Monte Carlo integration also doesn't work for high-dimensional parameter models that well. Yeah, it's really hard to get from there. So I've never seen a good comparison of either those methods for problems or those methods in comparison to what we will do tomorrow, which has a nice theory, namely variational inference. It's really unsatisfying. You see there are all these different methods, and most of the time, if you think in terms of simple models, it's you ask, why do I need them at all? And if it's a complex model, it's not that clear which method you then should follow. In a way that also reflects that these uses of, for example, variational inference or Monte Carlo integration in this Bayesian inference scenario, that's not that old, right? So to compute to do antiderivatives to compute definite integrals, that's I don't know, 200, 300 years old, and to do these kind of things, that's more like 50 years old, or in terms of variational inference, maybe even only 20 years old. So it's just not that well known when it is good and when it is not good. And so you don't find it in textbooks. So what is Monte Carlo integration? Here the idea is again to approximate integrals. So you have an integration problem, for example, finding the expected value of some distribution, or finding a normalization constant. And here the idea is to use random sampling. And this, as I mentioned yesterday from the history, this comes out of the World War II initiative and creating atomic bombs. So the Manhattan Project, that's where this originated, Metropolis. And the idea is, essentially, to use random support points in integrals, and then mainly the idea is to use also the law of large numbers that says the sample mean converges to the expected value. The expected value is a integral. The sample mean is something that you get from sampling. If you have many samples, that approximates an expected value. The expected value is an integral, so you approximated an integral by taking samples. So that's here the definition of a Monte Carlo estimator and the Monte Carlo algorithm. So if you have a continuous random variable C with a distribution P and a PDF small p, and you have a univariate real valued function f, then you might be interested in, or you can consider an integral of or you can consider the expected value of this random variable under this function, which is an integral. Namely, it's the integral of fx times px integrated over the space of x. So you have an integral here, and that's an expected value. Now, if you create independent copies of xi and sample from this distribution P, and maybe put these samples through the function, then you can, of course, compute the sample mean. And you know from undergrad statistics that the sample mean is an estimator for the expected value. Because the expected value is an integral, the sample mean here is also an estimator or an approximation of this integral. So the main point here is to realize that, or to again bring into your mind that an expected value is an integral. Now, if you can write some integral as an expected value, then you can use sampling and computing means to approximate this integral. So here the algorithm is then you create realizations from this distribution, and you compute the mean. That always, for me, so I will show you an example in a second, because for me it always shows, it's always like, I don't get the deepness of this. Yes, the sample mean can approximate or converges to the expected value, but what is with the integration? And let's look at an example here, because I think that makes that a bit clearer. So we consider this problem of integration. So we want to compute the integral of a function f from 0 to 1. So it's a definite integral that we want to compute here. So yeah, it's a definite integral. That would be, we want to compute, we have a posterior density, and we want to compute the probability for the parameter to lie between two values. Here, we're actually not doing that with a density, but with a different function, namely the function x squared. So we want to integrate x squared from 0 to 1. Of course, we can integrate the function x squared from 0 to 1 using antiderivatives, which is then shown here. We can form its antiderivative, which is 1/3 times x to the power of 3, because if you compute the derivative of that, you get to x squared. So we can solve this definite integral, of course, yeah, in the standard school manner, and get that it's 1/3. But for demonstration purposes, we want to here use a Monte Carlo approach to compute this integral. So what do we have to do to integrate this here using a Monte Carlo method? Well, we have to, okay, we have this integral here, so x squared from 0 to 1. We first have to realize that this integral can be conceived as an expectation, namely the expectation of this function here of x, namely x squared, of some distribution. The question is which distribution? Well, a distribution that has density function values of 1 from 0 to 1. So because x squared times 1 is still x squared. If we now conceive our 1 here as a probability density, then it's of course the density of the uniform distribution on this interval 0, 1. Yeah. So one has to find the random variable from which one wants to sample. One has to think a little bit in terms of figuring out to rewrite an integral as as an expectation. If we wouldn't have this on 0 to 1, but on 0 to 2, for example, then of course one would have to think differently, because then we wouldn't have, it wouldn't work with a 1. It would still work, but here it works very nicely because x squared times 1 is then x, because if you have the uniform wouldn't work. That's what I want to say. The uniform wouldn't work if you're on the interval 0 to 2, because that's not the value of the density of the uniform density on 0 to 2 is not 1. That's 1/2, because of course the uniform density needs to integrate to 1 on its support set. But here this works, and now a random variable with this outcome space 0 to 1 and probability density of 1 is of course the uniform distribution on 0 to 1. And if we now create samples from the uniform distribution and square them, then we know by the law of large numbers that the sample mean converges to this expectation if our number of samples, which is here denoted by m, gets very large. So again, we start with an integration problem that we want to solve. We rewrite this integration problem as an expected value by defining an appropriate random variable, and then we sample this random variable and compute a sample mean. So that's what I'm doing here. The analytical solution is 1/3 for this integral here, 0 to 1 of x squared. The Quadrature solution is also 1/3, and the Monte Carlo estimation of this integral approximation is 0.334, so almost 1/3. Here using 1,000,000 realizations of the uniform distribution on 0, 1, and then squaring these and taking the mean. So that's the logic of Monte Carlo estimation of integrals. So again, the problem is to make that as clear as possible. The problem is to evaluate an integral. Now, the next crucial step is to realize that expected values of random variables are integrals. So we start with not an expected value here, but with an integral that we rewrite as an expected value. And then if we have this expected value, then we can, of course, approximate this expected value by a sample mean if we get realizations from the random variable that this expected value belongs to, is with respect to. So that's the idea of Monte Carlo integration, Monte Carlo estimation. It's again numerical integration, and it works because the sample mean is a good estimator of the expected value. But again, the crucial thing is to realize that you can rewrite, but you need to do some thinking. You can rewrite integrals as expected values. So that's the crucial thing here. And then what is then another big part of numerical inference, which I now just highlight, is that using this approach to rewrite something like an integral as an expected value may lead you to random numbers that need to have a certain distribution for which you don't have a random number generator. And to do that, even if you cannot really generate random numbers from that, there are then different sampling methods, specifically acceptance rejection sampling is one of the core methods to create samples from some distribution if you don't have a random number, but you know how this distribution looks. So yeah, I think I'm exhausted, as you can tell from that my speaking gets more and more incoherent. I hope I could at least show you what Monte Carlo integration is about, or Monte Carlo estimation, that sometimes is used interchangeably. The point is that you rewrite integration problems as expected values and approximate expected values by sample means. That's the whole point there. What the reason why I never really went too deep into numerical inference, as you might can tell from also what we looked at here, is it's not a coherent thing. So there's a coherent problem. There is the problem of evaluating integrals, but there are different ways to approximate integrals. Quadrature, using an analytical approximation like Laplace approximation, using random sampling. And all these methods have not really been designed for Bayesian inference. They have been designed to approximate integrals. So these methods don't feel really like deep into Bayesian inference. They are just ways to do Bayesian inference if it comes to computing integrals. Variational inference, on the other hand, which is the topic tomorrow, really feels much more connected to the problem of Bayesian inference. Oops, jetzt gehen wir schon wieder Nachrichten. So variational inference is much closer to Bayesian inference, I always find, than these kind of numerical bits and pieces that you can use to use Bayesian inference. So with that said, I hope I motivate you a little bit to also attend tomorrow. So I really like variational inference a lot more than numerical inference. And it's also how the brain works. It's the free energy principle. So that's why it's interesting to learn about variational inference. Good. Any questions this afternoon for this afternoon session? I know that wasn't. Yep.
Oh, sorry,
no,
please.
Go ahead.
Okay, sorry. Just for the very last part that you explained about Monte Carlo integration, could you again quickly summarize the intuition behind rewriting integrals as sort of expected values?
So the intuition is that, the point is that sample means are estimates of expected values. Yeah. So if you want to estimate the expected value of a Gaussian, you generate samples from the Gaussian and you compute the mean, and that's then an estimate of the expected value. So that's what you've been doing in statistics all the time. Now, an expected value by definition is an integral. And now if you have another integral that you want to solve and that you can rewrite as an expected value, then you already know how you can numerically estimate this integral, namely by sampling. So that's the. So I think the crucial thing, especially specifically, depends on how deep you are into probability theory. If it's somehow novel to you that expected values are integrals, then it's so if expected values were not big in your statistics teaching because you didn't do much of probability theory, where expected values, of course, are very important, then it's a little bit surprising that you can use sampling and computing sample means for solving integration problems. But if you internalize that expected values are integrals, then basically you can just then instead of defining an expected value as an integral, you can say, okay, we rewrite an integral as an expected value, and then sampling and using sample means makes sense. So that's my intuition there.
Yeah, I think it was really that part that we didn't have like in our statistics courses. Like I never saw it from that angle, you know, or it wasn't. Either it was taught in a way, but I didn't pay attention to it because I thought, yeah, it's not relevant anyways, you know. So, but it is in the end. So that's sort of my problem in that way. But yeah, I think I will read up on that particularly again.
Yeah, so it's the question is, what is an expected value and what is probability theory? So that's this is, of course, this Monte Carlo integration makes sense if one is familiar with probability theory and the notion of what random variables are and what their expected values are and how they are defined. Then it makes sense. If one is not familiar with probability theory that much, then it's of course a big question of why sampling can be used for integration. But yeah, so expected values and variances are integrals, and they will be introduced in the winter term. I don't know, briefly before Christmas, I think. It's not the first thing that you do in probability theory, but it's definitely also not the last thing, because the last thing is always transforming random variables and expected values. They are, of course, expected values and variances are useful summary. So again, now going a little bit out of things, of course, probability and probabilistic models are models for real world phenomena, but they always then, if you have a distribution, they are functions. So you have like the Gaussian, and you might want to give single number summaries of these models, and these are expected values and variances. So that's where they come in probability theory. All
right. Thanks a lot.
Good. Then see the two of you maybe hopefully tomorrow at 9 with a nicely coherent topic on variation inference. Bye-bye.